Hi, this is week 12 of chemistry, and in today's lesson we're going to go ahead and go over what is polarity, how to identify if a molecule is polar or non-polar, and we're also going to see how polarity affects the characteristics of a molecule. So let's go ahead and get started. Our first polarity says molecules that have a positive and negative end are referred to as polar molecules. So one side will be positive, the other side will be negative. What causes this positive and negative end? Well, that is caused by the uneven sharing of electrons within a bond. So when one atom is more electronegative than the other atom, those electrons within the bond will go towards the more electronegative atom. And that's what's going to create that slight positive and slight negative charge. Alright, so we're going to go ahead and take a look at 4 different examples and identify them as polar or non-polar. Alright, so our first one is HCl, and here's the Lewis dot diagram for this molecule. There's our one bond. Now within that one bond there are 2 electrons. Now between hydrogen and chlorine, chlorine is more electronegative than hydrogen. So what that means is that the electrons will be closer to the chlorine. So we draw an arrow with a line at the end showing you the movement of the electrons. So the electrons move towards the chlorine because chlorine is more electronegative. So it can pull on those electrons more than the hydrogen can. How do we know that chlorine is more electronegative? Well, if you go back to the lesson on periodic trends, you'll know that as you go towards the top right corner of the periodic table, those elements will have the highest electronegativity. That means they'll have the ability to pull on those electrons a lot more than atoms on the other side of the periodic table. So that's how I know chlorine is more electronegative than hydrogen. So since the electrons get pulled towards this side, the right side will develop a slight negative side, and the left side will be slightly positive. Now, by the way, that is a symbol for a Greek letter D, which means it has developed a small negative and positive side. Now this molecule right here, I would refer to it as a polar molecule. For our next one, it's H2O, water. And again, we have now 2 bonds. So we're going to have to draw an arrow for each one of those bonds. And oxygen is more electronegative than hydrogen. Again, I use the periodic table as my reference. Oxygen is closer to the top right corner than is hydrogen, so therefore it's more electronegative. So I know that the electrons in the bond are going to go towards the oxygen. So for this bond here, I'm going to go ahead and put an arrow going towards the oxygen, and I'm going to do the same on this side. Now, that means that all the electrons are going towards this corner. This side will develop the slightly negative side because the electrons are negative and the electrons moving in that direction. And this side will then develop the slightly positive side. So this molecule will also be referred to as a polar molecule. Now, our third example is carbon dioxide, CO2. Here's the Lewis dot diagram for it. It's got double bonds, but it still follows the same behavior. Here, oxygen is more electronegative than is carbon. So for this bond here, the elements are going to move towards the oxygen, and on the other side, the electrons are going to go ahead and move towards the oxygen as well. Alright, so is this polar? They actually, no, it's non-polar. Why is it non-polar? Well, although electrons are moving this way and that way, notice that these 2 arrows are moving against each other and they cancel out. So these 2 cancel each other out, so that's why we end up with a non-polar molecule. Each bond you can refer to as being a polar covalent bond, but for the whole molecule, no, these 2 cancel each other out. Compare that to the first one. Did anyone cancel out this arrow? This is no, there was only one arrow. There was no second arrow to cancel it out. What about in our second example? These 2 arrows, one's going side to side, the other one's going up and down. So again, they do not cancel each other out, so that's why we ended up with a polar molecule. But for this one, both arrows are in the same line. They line up with each other, and they're going away from each other. They cancel each other out, so carbon dioxide will be a non-polar molecule. Next, CF4, carbon tetrafluoride. For this molecule, again, we have our Lewis electron dot diagram. Fluorine is more electronegative than carbon, so the electrons are going to move towards the fluorine from the carbon. So in this bond, they're going to move towards the fluorine. And same thing here. They're going to do the same. Notice that they're going away from each other, so they cancel each other out. And for this bond, the electrons are going to move towards the fluorine. Same thing on this side. And again, these two arrows, they're going against each other. They cancel each other out. So these two cancel each other out. Those two cancel each other out. Every single electron movement is canceled out. Again, this one, I would classify it again as a nonpolar molecule, since all the electron movement get canceled out. Now, drawing the Lewis dot diagram is very helpful and essential to actually figuring out whether the molecule is polar or nonpolar. Now, something that you're looking for also is, another way of doing this is looking for symmetry within the molecule. If you have a molecule that is symmetrical, then that will be a nonpolar molecule. What I mean by symmetrical? Well, a symmetrical molecule will look the same on both sides. So for example, if you look at this molecule of carbon dioxide, the left side looks identical to the right side, and the top and bottom look the same. So that is a symmetrical molecule. So I can already say, oh, that's nonpolar. If both sides look the same, top, bottom, left and right, then it's a symmetrical molecule, so it is nonpolar. Same thing for this molecule. If you look at the right side versus the left side, they look the same. And same thing for top and bottom, they look the same. So therefore that is a symmetrical molecule, and symmetrical molecules are nonpolar. On the other hand, if a molecule is asymmetrical, both sides do not look the same. For example, let's take a look at water. The left side of water and the right side of water do not look the same, so that's asymmetrical. You can say it's polar. And also true from the top and the bottom of the molecule, they don't look the same. So that is a polar molecule, is asymmetrical. For this one, does this side look like that? No, they do not. They don't look the same. So it's an asymmetrical molecule, so therefore it's a polar molecule. Going forward, we're going to go ahead and take time to identify every single shape, and we'll be looking for their symmetry. If a molecule is symmetrical, then that molecule is nonpolar. But if the molecule is asymmetrical, then you have a polar molecule. Hi, up next for us, we're going to go ahead and do a quick review of all the names of the shape for the Vesper models of the atoms. So we're going to go ahead and begin up here with linear, and it has 2 shared and 0 unshared pairs of electrons. Trigonal planar has 3 and 0, so you can see the 3 lines representing the 3 bonds. No unshared pairs of electrons. Bent here has 2 shared electrons, so the lines, and 1 unshared pair, so that's why you see 2 and 1. Tetrahedral is 4 and 0. Trigonal pyramidal is 3 shared, 1 pair unshared on the top, so it's 3, 1. Bent is 2 and 2 for shared and unshared pairs. Trigonal pyramidal is 5 and 0. Seesaw is 4 and 1. T-shape is 3 and 2 for shared and non-shared pairs of electrons. Linear is 2 and 3 for this type of linear, and yeah, linear does come up multiple times. Same thing as bent here and there. Moving along, octahedral has 6 shared and 0 unshared. Square pyramidal, it's going to have 5 shared and 1 unshared. There you see it. Square planar is 4 and 2. So there you see that drawing. T-shaped, yeah, again, it is 3 and 3. So that's the picture for it. And finally, last one, linear one more time. It's going to be 2 shared, 4 unshared. That would be linear. So you see 2 and 4 for the shared and unshared. Now, although these drawings are nice, they are 2-dimensional drawings, so we can't really use them too much to visualize exactly what an atom looks like. So instead, we're going to go ahead and use these models a little bit, and we're going to use them to figure out whether our molecule is polar or non-polar. That is our goal. If a molecule is symmetrical, that means that you have a non-polar molecule. But if it's asymmetrical, that means that you have a polar molecule. Symmetrical meaning both sides look the same. Asymmetrical, both sides do not look the same. And for three-dimensional structures, it's going to get a little bit difficult, but we'll work through it. Alright, so we're going to start with the first one, linear. In linear, here you have the central atom with this white atom right here, and the purple represents the bonds right here. So keep that in mind, the purple represents the bonds. So let's say that the electrons move towards the bonds. Notice it's a straight line, so therefore this one's symmetrical. The left side and the right side look the same. So we're going to say this molecule linear is nonpolar. Now I can make the same claim for all the linear molecules. All of our linear molecules are going to be nonpolar as well, because they all end up looking the same. Even though it has electrons around, it's going to end up being nonpolar. But we'll get more into detail with those. Our next one is trigonal planar. And this is what our trigonal planar molecule will look like. And it is symmetrical. Symmetrical because if I were to get this to spin, would it be balanced? Sure. You're like, but the top and the bottom don't really look the same. No, but it is well balanced. Alright, so this is a symmetrical molecule. It could easily spin, and it's very well balanced. So if it's symmetrical, then you say it's a non-polar molecule. Alright, now let's talk about the next one, bent. Alright, so going back to our trigonal planar molecule, now I'm going to replace one of the bonds with an unshared pair of electrons. So, using the gray, I'm going to go ahead and put it right here, and there it is. So this is our trigonal planar, still bent. You see that bent shape, but in gray, that's a pair of electrons. And the electrons, well, it's easier sometimes to envision as not being there, but if you're wondering why doesn't it become straight, well, they do push the two bonds to be bent, alright, but picture is not being there. And I ask you, is this symmetrical? Could I easily spin this? If you had a fan with one blade broken, could it easily spin? This is no, this is not symmetrical. The top and the bottom don't look the same. So therefore, this one would be a polar molecule because it's asymmetrical. Up next for us is our tetrahedral. And for a tetrahedral, I'm going to go ahead and pick up their tetrahedral. Here we go. This is what it looks like. And for a tetrahedral, it's got four sides. And again, notice the molecule is much better than my drawing because the drawing is two-dimensional, but the molecule is a three-dimensional molecule. Alright, for this one, it is very well balanced. If I could spin it, if I were talented enough to spin it, I could get it to spin, and it would be symmetrical. So because it's symmetrical, you say, oh, that's non-polar. Symmetrical means that the left side and the right side look the same, and the top and the bottom look the same. See, it doesn't matter which way I turn it, there's always one pointing up, so it looks the same. Alright, our next one is trigonal pyramidal. So what I'm going to do for that one is remove one of our purples, which is a bond, and replace it with an unshared pair of electrons. Alright, so that's an unshared pair of electrons. Does the top and the bottom look the same? No, they no longer do. Notice that now this one is an unshared pair of electrons. So again, it's sometimes easier to envision it as not being there. So does the top and the bottom look the same now? This is no, it does not. So this is an asymmetrical molecule. So therefore, we're going to say it is polar because it's asymmetrical. Now, going along the same line, our next bent, bent comes up twice. We're going to remove another one of our bonds, and again, we're replacing them with unshared pairs of electrons. And you can see how the purple still a bent shape. It's not a straight line, and that's why we call it a bent. So if you're wondering, isn't it a straight line? No, it's not. Alright, now again, does the top and the bottom look the same? No, we have gray and white. No, they don't look the same. And so it's asymmetrical. Asymmetrical meaning that it's a polar molecule. Alright, for us next is trigonal pyramidal. And for trigonal pyramidal, we're going to go ahead and use our trigonal planar, which was nonpolar, and what we're adding on top is another bond on the top and another bond on the bottom. Alright, so this is what it will look like. And yeah, the top and the bottom are symmetrical, and everything is symmetrical. The sides are symmetrical. If I were talented enough to get it to spin on my finger, it would easily spin. Alright, so that would be a trigonal pyramidal. It is symmetrical, so therefore it is non-polar. Next is seesaw. So we're going to get one of the sides, and we're going to go ahead and remove it. And once we do so, replace it with a pair of unshared electrons. So again, picture them as almost not being there. It's a lot easier. And now, could I get this to spin and stay on my finger? No. Why not? Because it's an asymmetrical molecule. It doesn't look the same on both sides. So therefore, I would say that's a polar molecule. Let's go ahead and continue. What if I remove another one of these? Alright, now we got two unshared pairs of electrons. And our two unshared pairs of electrons, again, that would be our T-shape. So that's this one. Three shared, the three purples, two unshared here in white. And does it look the same? Again, when you're visualizing it, does it look, the left side and the right side look the same? This is no. This one has a bond, that one does not. So therefore, this is an asymmetrical molecule, and our asymmetrical molecule, that is polar. Lastly, I'm going to go ahead and do one last replacement. All right, take away the bond. And this one has three unshared pairs of electrons, so I put them here in gray. And there are three unshared pairs of electrons. But if you look at it now, the top and the bottom do cancel each other out. And again, it's easier to visualize whether it's symmetrical or not when you ignore those unshared pairs of electrons. It looks just like a linear. And it is. So linears are non-polar, because it is a symmetrical molecule. Alright, last we're going to go ahead and go to octahedral. And for octahedral, I have this molecule. And for this molecule, I'm going to go ahead and, if you look at it again, if I were talented enough to get it to spin on my finger, it would spin there because everything is pretty much well balanced. That's an octahedral. So it's symmetrical, the top and the bottom look the same, the left and the right, the front and the back look the same. So therefore, if it's symmetrical, it's non-polar. But the next one, square pyramidal, now I'm going to remove one of the bonds, replace it with an unshared pair of electrons here in gray. And do they look the same? No, again, the unshared pair of electrons may be easier to visualize without them not being there. Alright, so does the top and the bottom look the same? This is no, they don't. So that is asymmetrical, so that's a polar molecule. Next, square planar. I'm going to remove the bottom. So I've removed the bottom. In their place really is a pair of unshared electrons at the top and the bottom. Now again, does the top and the bottom look the same? It's like, sure, we got gray, and the side purple. So what would this one be? This one would be non-polar because it is symmetrical. It means top and the bottom look the same. Alright, moving along, T-shape. Now I'm going to take away another one of these and just focus on the purple. Just look at the purple. Do the left and the right, do they look the same? And this is no, they don't. Alright, so this one would be a polar molecule because it's asymmetrical. And finally, the last one, we go ahead and we replace. Last one. And we end up with this shape. Alright, now the top and the bottom do look the same. It's a linear one more time. So this one will be a symmetrical molecule. If it's a symmetrical molecule, therefore it is non-polar. So I'm going to put an N for that. Alright, so we have identified all of the Vesper shapes as either polar or non-polar. So here they are. Up next for us, we're going to go ahead and work with molecules to identify them as either polar or non-polar. So let's get started. Here are three molecules we're going to try to identify: HBr, CF4, and finally Bi3. Alright, so our first one, HBr, hydrogen bromide, is none of these actually, none of the Vesper shapes, because this one only has one bond. Most students will confuse it for this one as linear, but this one's got two bonds, this one's only got one. Alright, when they only have one bond, all you really care about is their electronegativity. Hydrogen and bromine don't have the same electronegativity. Bromine is more electronegative, so that means the electrons will go towards the Br, the bromine. So I'm going to put an arrow showing the movement of the electrons, And since this arrow does not get canceled out, that is a polar molecule. It is not symmetrical, so it's an asymmetrical molecule. That's a polar molecule. All right, moving on to this one. This one is a tetrahedral. How can you easily identify it? Well, if you look at the central atom, it's got 4 shared electron pairs and 0 unshared, so 4, 0. Notice that that is the only combination for a tetrahedral, and here we've already identified as nonpolar. So I'm going to put carbon tetrafluoride as nonpolar. Last one, Bi3. Bi3, again, we're going to go ahead and look at the central atom, and the central atom's got 3 shared electron pairs and no unshared electron pairs. So that's going to go ahead and take us to trigonal planar, which is N right here for nonpolar. That's a nonpolar molecule. So those are the answers for our first 3 examples. For our next group of 3 molecules, we're going to go ahead and take a look at NF3, CaCl2, and PbR3. Alright, so this is nitrogen trifluoride. Here's a molecule, and we're going to look at the central atom again. How many shared electron pairs? You see the lines? Those are 3 shared electron pairs. And on the top we've got 1 unshared pair of electrons. So it's 3, 1. So now looking at the Vesper diagrams, who is it? It's trigonal pyramidal, which is a polar molecule. Next, CaCl2, calcium chloride. In calcium chloride, it's got only 2 shared pairs of electrons and no unshared pairs. 2 and 1, 2 and 0, that is linear, which is a nonpolar molecule. Lastly, PbR3, that is phosphorus tribromide, and in this one we have the same as our original molecule that we started here, 3 shared, 1 unshared pair on the top, 3 and 1. That goes ahead and gives us trigonal pyramidal, which is a polar molecule. So we have polar, nonpolar, and polar molecule. The next group of 5 molecules we'll be looking at are as follows. PCl5, which is phosphorus pentachloride, SF4, which is sulfur tetrafluoride, and finally ClF3, which is chlorine trifluoride. Alright, so the Lewis dot diagrams for them are right here. We'll be focusing on the central atom to identify which Vesper shape it is, and therefore we'll know if it's polar or non-polar. So here's our first one, PCl5. That P, the phosphorus, only got 5 shared electron pairs but no unshared electron pairs, so 5, 0. For that one, that would be trigonal bipyramidal, which is a nonpolar molecule. So, and for that one, our next one is this one. The S as a central atom has 4 shared pairs of electrons and 1 unshared pair of electrons, so 4 and 1. That will be our CSO, which is a polar molecule. So there's our answer. And finally, our third molecule for this set is this one, which is 3 shared pairs of electrons and 2 unshared pairs. So it's going to be 3 and 2. So for 3 and 2, that's going to go ahead and be T-shaped right here, which is a polar molecule. So that goes ahead and gives us the answer for these 3. And for our last group of 3 examples, we have BRF3, XeF4, and SCl6. So let's go ahead and identify them as either polar or nonpolar. So for this first molecule, BRF3, that's a bromine trifluoride, we'll look at the central atom and see how many shared and unshared pairs of electrons it has. So it's got 3 shared, 2 unshared pairs of electrons there. So 3, 2, that's going to go ahead and be T-shaped, which is a polar molecule. So our answer for this one is polar. Next, we have XeF4, xenon tetrachloride. Xenon tetrafluoride. And let's count how many shared and unshared pairs of electrons are on the central atom. So you see the 4 lines right there. That's going to be 4 shared. And unshared, we have 1, 2 pairs. So 4, 2. That's going to go ahead and give us square planar, which is a nonpolar molecule. And finally, SCl6, which is sulfur hexachloride. And for the central atom, the S, so that's 6 shares, 0 unshared. So that's going to go ahead and be octahedral, which is a nonpolar molecule. Alright, so that is how you can use the shared and unshared pairs of electrons plus the Vesper shapes to go ahead and figure out whether a molecule is polar or nonpolar. Up next for us, we're going to go ahead and take a look at how polarity affects the characteristics of a substance. So we're going to be looking at forces of attraction. So first of all, dipole, which is another word for a polar molecule, a dipole, is a molecule with a positive and negative ends. That's a polar molecule, so a dipole. Now, if the positive and negative are very strong, they're able to stick to each other quite a bit. But if there's weak attractive forces, they can separate easily. Alright, and that's going to affect three different things that we'll be looking at. Number one we'll be looking at is this one, volatility. Volatility refers to how easy a substance evaporates into the air. So right here it says volatility is the measure of how easily a substance evaporates. Polar molecule have low volatility. These molecules, they stick to each other quite a bit. So if you have very strong attractive forces from polar molecules, then they're going to stick to each other. And even though you're supplying a substance with heat, it's going to have very low volatility. Very little will evaporate. On the other hand, if a substance has very weak attractive forces, those molecules are not sticking to each other very well, so they're going to separate easily. And you can see that as a lot of steam coming out of this. So you will refer to that as having high volatility because it is evaporating a lot. Our next substance we'll be looking at is viscosity. Viscosity is a measure of how easily a liquid flows. So viscosity is the measure of resistance to flow. Polar molecules tend to have high viscosity. So if you have very strong attractive forces, then it's going to resist flow quite a bit because again those molecules are attaching themselves to each other. So and a great example of that would be honey. If you've ever poured honey, you know it pours very slowly compared to water. So water in this case would be weaker than the honey. So I have it here as weak attractive forces. It pours out much more easily. So the honey would have high viscosity, high resistance to flowing. The third one is surface tension. Surface tension is a measure of the inward pull by particles of the interior. So again, these molecules are attaching themselves to each other. They pull each other. Polar molecules tend to have high surface tension. How much surface tension? If you see in the picture right here, you can actually get one of those small paper clips, and if you gently place it on top of a cup of water, the paper clip will stay on top. I don't want to say it floats because it really does not float. It is more like sitting on top of the water. Why isn't it floating if it's on top of the water? Well, if you poke on it and push it down below the surface, it will sink to the bottom. Substance that floats would come back up because it floats. So it actually sits on top of the water because of the surface tension. So if a substance has high surface tension, you can put a paper clip on top, then you can deduce that it has very strong attractive forces. On the other hand, if you put the paper clip on top, it just sinks every time. Then you can say, well, it's got weak attractive forces, so that's why the paper clip cannot be held by those molecules. For our last topic, we're going to go ahead and discuss hydrogen bonding. Hydrogen bonding is a special type of bonding that occurs between molecules. Now, this type of bonding requires the following. It must have a hydrogen atom attached to either a nitrogen, oxygen, or a fluorine. So here we have nitrogen, oxygen, fluorine attached to a hydrogen. On top of that, you also require a pair of unshared electrons attached. And once you have those conditions, then you can go ahead and get a very strong attraction between molecules. Alright, so now let's take a look at these four that are given to us. Here's the molecule H2CO, H2O, NH4 plus 1, and NH3. Which one of these will be able to form hydrogen bonding? So if we go ahead and do the dot diagram for it, we say, could this form hydrogen bonding? The answer for this, no, it cannot. Why not? Because the hydrogen is attached to carbon, and to form hydrogen bonding, you need to have hydrogen attached to either nitrogen, oxygen, fluorine. So does this form hydrogen bonding? The answer is no, it does not. Alright, this next one, can water form hydrogen bonding? And the answer to that is yes, it can. Notice that you need an oxygen with a hydrogen, which it has, and it also has at least one pair of electrons. In the case of water, it's got two. So, can it form hydrogen bonding? Yes, it can. Next one, ammonium, NH4 plus 1, could it form hydrogen bonding? You need hydrogen attached to nitrogen, and it does have it, but another condition is that it must have a pair of free unshared electrons, and ammonium does not have it, so no, it cannot form hydrogen bonding. Alright, the last one is ammonia, and ammonia does have the nitrogen and the hydrogen plus the unshared pair of electrons, so ammonium would be able to form hydrogen bonding, which is again a special type of attraction between molecules that is very, very strong. Alright, so those are the molecules that can and cannot form hydrogen bonding. Now, we've covered in this unit 2, the periodic table, periodic trends. We also talked about the distribution of atoms around an atom. We talked about the Vesper. We also talked about how to draw Lewis dot diagrams with expanded octets, with double bonds, triple bonds, with charges, without charges. And now we finish up with attractive forces and polarity. So this concludes this lesson for week 12, plus this also concludes unit 2. Thank you so much for watching.